Hello, I'm Khalid Ajran, and today I'll be presenting my research that I've done with the Search-Based Planning Lab this summer as part of the RISS 2023 program. The name of my research is Conflict-Based Search with Relative Constraints for Multi-Agent Pathfinding. Now, the motivation behind our work this summer is a classic problem in the field of planning, which is the multi-agent pathfinding problem. And in this problem, the goal is to find a set of paths for a bunch of agents in a common environment that leads each of them to their different goals with the minimum cost possible. And given that this is a pretty simple problem in concept, it has loads of applications in the real world. And some of these applications are robots moving around in a warehouse trying to get boxes to different locations. You can also apply this problem to traffic control, or you can even apply it to video games where you might want some characters to avoid colliding with each other as they move around. So our algorithm builds on an existing algorithm called the conflict-based search, or CBS for short. And this is an optimal algorithm that solves the MAPF problem. It does this in two levels. In the high-level search, it imposes some constraints on the individual agent's paths so that when the constraints accumulate, it leads to solution for the MAPF problem in general. And in the low-level search, the algorithm finds paths for each agent within the environment that satisfy the constraints from the high-level search. And by having these two searches work in tandem, the algorithm finds an optimal solution. So our work this summer focuses on a specific area of improvement within this algorithm, which I will show with an example. The CBS algorithm usually uses space-time constraints, which simply require that an agent avoids a specific location at time t. So what the algorithm might do, it might find these initial paths here for these agents, and it's going to see this conflict between the red and blue agents. And so it's going to add a constraint to one of them to prevent them from taking this location at time one. So it might put a constraint on the blue agent to avoid this location, and now the blue agent will have to find a different path. And let's say next up, the algorithm looks at this conflict between the red and green agents, which happens at time 4. And let's say that this algorithm adds a constraint on the red agent to avoid this location at time 4. And now we have something that we thought was inefficient. This constraint that we added on the blue agent is no longer needed. We put it there in the first place because we wanted the blue agent to avoid the red agent at time 1. But now that the red agent changed its path entirely, this constraint is preventing blue from going to a location that it should be allowed to go to. And so this is slowing down the search. What we'd like to happen instead is that when red changes its path to this path instead, we want the constraint on the blue agent to move along with it. And now the blue agent would be able to take the direct path to the solution here. So we tried using some constraints that don't depend on a specific location, but instead depend on the relationship between two agents. The constraint types we found most promising are avoidance constraints, which come in the form of A, B, T. And these constraints require that agent A and B are at different locations at time t. Another constraint we considered is the priority constraint, which is, it also comes in the form of A, B, and T, but it is slightly different from the avoidance constraints in that agent A has higher priority than B at time t, which means that B has to avoid A's location at time t, but A can ignore B's location at time t. And finally, the doubled priority constraints are very similar to the priority constraints, but when A gets priority over B at time t, it gets priority for both the vertex and the edge that it traverses at time t. So the results show that our algorithms do pretty well against the baseline algorithm. Um, just like to give a note, the most time-consuming part of the search is expanding high-level nodes in the search. And so we'd like to reduce the number of high-level nodes expanded. And so if you look at these two maps here, this is a random map with some obstacles scattered randomly, and this is an empty map. And as you increase the number of agents in the environment, you can see that our algorithms reduce a notable amount less high-level nodes, and this is going to make the search faster. Um, and while the results are nice on just generic maps, they look much better on small dense maps. In these maps, they're much more claustrophobic, and it's harder to find a solution. So you can see here that the baseline algorithm is expanding quite a lot of high-level nodes in these maps, while our variant algorithms are expanding notably less, like a few orders of magnitude less. And especially the most promising variants are the ones using the avoidance constraints and the doubled priority constraints. So our analysis is that the theoretical guarantees are much trickier this time around. The fact that these constraints are relative instead of the usual space-time constraints makes it much harder to pin down a proof for why this algorithm always works. And in particular, there is a useful property in the original proof, which is that the search has kind of Markov property, in that at any time the search doesn't depend on like how it got here. It just depends on like the current state of the search. But now the search is dependent on its history. But despite this, the experiments show that all our variants are still complete and optimal. Whenever there is a solution, the variants find it, and they find a solution with the same costs as the usual CBS algorithm. So the main conclusions and takeaways from this is that our relative constraints are really effective in dense scenarios where you have a large number of conflicts. So these small maps fit that bill. And more generally, if you want to approach like this problem in a similar way, you could take the CBS framework and use a different kind of constraint. And this can have some very promising results, as we just saw. And lastly, we advise people doing future work to try and get deeper within these theoretical guarantees, or to explore some different constraint types that we can apply instead of our relative constraints. Thank you very much for listening.